Well, I know you can't hear it. We're trying this again. Oh, boy. Anyway, good evening, everybody. Welcome to Saturday Night Rabbit Hole. Waiting for the guest to come on right now. And we're going to talk about earthquake structures from Lompoc to San Francisco today on the western side of the San Andreas. So there's several areas there. Canuck, I can hear you. Is probably you got JSL on right now.
Too many things going on.
Yes, sir. Yes, sir. Too many things going on. He's sticking his face in it. So no, he's not motorboating. He's just sticking his face in it.
There.
All righty then. Let me show everybody what we're going to do today. This here's Lompoc on here. It's north of Los Angeles, north of Santa Barbara. The Garlock Fault goes right through here. What today we're going to do, this is the San Andreas all the way up to San Francisco. We're going to talk about this block of fault systems right here, west of the San Andreas. And then several of the notable ones, and then we'll talk a couple of earthquakes as well. I think we'll save the earthquakes until the end because it will help you understand what's going on here, and so you all can be on the same page. What the frack? Start recording. Okay, so back again for those on JSL. We are JSL is twitch.tv/Joe Slig Live. Okay. San Andreas is right here. This is Lompoc. This is San Francisco up here in the north. We're going to talk about all the fault systems that are working on the western side of the San Andreas, i.e. on the northern Pacific edge, north of Los Angeles and north of Santa Barbara. So we're going to talk about these tonight. There are some interesting aspects to these fault systems, three main fault systems, and they have, tails that are 240 miles long, and some of them can produce really high quakes. And we're going to talk about some of this stuff tonight here on the Rabbit Hole on Saturday. So this one's titled Fault Structures of Lompoc to San Francisco Fault Structures. All right. Today is November 9th of 24. All right. Good evening there, Canuck. I see that you made it. You're
I'm here.
You're gargling with them. What do you call them? Kit Kats?
Yeah.
Yeah. All righty.
My water's not good.
You got your water?
Yeah.
All right, bud. Let me see if I can. Yeah. Anyway, so this is the map we're going to be using. We've been using this map for some time now. It's not all inclusive, but it's pretty much everything we're going to talk about. And so let me zoom on down. As we zoom in, the Garlock Fault is this orange line right here. The San Andreas is this big red monster. Tejon Pass is right here. This Fraser Mountain, it's all this purple. There's a fault zone right here. It's called Big Pine Fault System that comes out and turns north. We've got the Lion's Head Fault, the Casamilla Fault, Los Alamos Fault down here, the Santa Maria Fault Zone, and the Edna Fault Zone, and the east, Hasina Fault, Huasina, Hasina Fault. I'm going to call it that. I don't know. And primarily, we're going to be watching this one because it's interior of all these. But as you see down here, it actually has some other faults that go north of it. South Cayuma Fault and the Panza Fault and the San Juan Fault. And you can see the Morales Fault right here, which is underground. You can't be seen on the surface. Actually, looks like it turns right into the White Wolf Fault, doesn't it? Mm-hmm. And the Big Pine Fault looks like it used to belong to the Garlock, Northern Garlock branch fault right here. And there's a mess right here. And we'll explain kind of how come these faults exist. As we get, as Hassem, we already talked about these, yeah. Casamia Fault. Out here, we already talked last time or a few times ago about the Santa Ynez Fault system that branches off into these other ones like Casamia, Lion's Head, Santa Ynez River Fault, Pacifico Fault, and then you can see the Santa Ynez Fault. That's a major fault system that splays out into the sea. Out at sea, we got a Hossagari Fault. That's Hosgri. That's offshore. And it kind of comes in with a bunch of splays and hits the San Simeon Fault and continues to go north into the Palo Grande, Colorado Fault, Palo, Colorado Fault, and the San Gregorio Fault. There's an Ascension Fault on the outside of that. I don't know what this one is out here. As a quaternary fault, we don't know. It's unnamed, I guess. There's a structure discontinuity up in here. We learned a little bit about discontinuity in the class today. If you didn't see the class today, it's a really good one. We'll talk about that sometime. Santa Lucia Fault Bank is out here. That's a major fault system. And Paleo subduction zone way out here. Having a subduction zone off the coast of California is kind of interesting to me. But I think the Paleo subduction zone, thrust fault way the hell off coast. And it's really interesting that we have one of these way out here. The fact that it's a thrust fault, we're going to talk a lot about thrust faults. And I was trying to get some information for you and regarding these fault systems. And I ran into a whole bunch of information that would probably detract from what we're going to do tonight. We got a big night, so Canuck, good evening to you. And I hope you're okay now that you had your Kit Kat. And I think I've laid some foundation for us where we're going to be west of the San Andreas. And this is the Pacific Plate, by the way. The American Plate's over here. So we're going to stay on the Pacific Plate tonight.
Yeah. So we're going to start tonight by doing the major offshore.
Offshore, the Hossagari Fault.
Yeah, Hosgri and San Gregorino.
Yeah, okay, Hosgri Fault Zone. The Hosgri Fault Zone's made up of a little tiny fault zones. As you can see, they're all part of the same thing. Hossagari Fault, it's definitely certain type. I don't know what kind of fault it is. Do you know what kind of fault it is? I guess we'll find out right here. The Hossagari Fault is offshore fault zone located near the central coast of California in San Luis Obispo County. The main fault stretches about 87 miles and is located nearest the coastal communities of Cambria, San Simeon, Morro Bay, Baywood Park, Los Osos, and Avila Beach. The fault system includes its branches and is some 260 miles long and is a right lateral strand of the San Andreas Fault system. The Hossagari Fault is comprised of the component of the San Andreas, and its movement is primarily reversed thrust, which is interesting. We have to look that up, and as well as it exhibits right lateral slip, and is thought to be capable of generating earthquakes up to 7.5. In November 4th, 1927, Lompoc earthquake, a magnitude 7.1, is thought to have occurred, but it's uncertain if it's on this fault.
So we
And-
talked about that Lompoc quake before.
Right.
They're unsure if it was exactly on the Hosgary fault or one of the other ones that comes off there.
Right. Comes off right in front of Lompoc there. Yeah.
Yeah.
Happened on November 4th at 5:49 Pacific time. An epicenter off Santa Barbara County. It measured 7 or so. Maximum intensity was 9 or violent. It caused widespread damage in several towns of Santa Barbara County. And a 6-foot, 7-inch tsunami damaged the railroad infrastructure that was recorded in Hawaii. And there was no injuries or deaths from this earthquake. So, yeah, that's pretty wild. Seismologists of Kenji Saraki and Paul G. Somerville determined the earthquake's epicenter to be somewhere out there. Based on their analysis of tsunami arrival time, they estimated that the moment magnitude to be a 7. The tsunami magnitude 7.6 derived from the tsunami observations in Hawaii was deemed an overvalue. The fault responsible for the earthquake was a north-northwest trending structure located about 25 miles offshore and west of Point Concepcion. The earthquake's focal mechanism indicated that the exclusively reverse faulting mechanism. No specific fault have been associated with this earthquake, but its location places it near and about the southern segment of the San Lucia Bank fault system. Another possible source, though, in uncertainty, is a Hosgary fault, a northwest dipping oblique reverse fault. So it's up in the air whether or not this earthquake in 1927 was on one of these two areas. Nobody had to, triangulate it in there, so it made it a little tough.
So we've already talked about that one before.
Right. That's why I went ahead and read it.
Yeah, Santa Barbara.
The Hosgary fault component. There is a Diablo Canyon power plant out there. I'm not sure. I thought they shut it down.
I don't know if it's still operating, but when the video I just watched about the San Simeon quake, the fire chief was talking about it. But he was the one that was in charge of the response to 2003. So he said they had to send like a bunch of people there to check it.
Yeah,
but he never said if it was still. And the presentation I watched was from the end of last year, 2023. But he never.
Oh, okay. So it's relatively new stuff.
Oh yeah, it was super interesting because the USGS guy that was on there had like where all the aftershocks were, and it was on 2 different faults, one going northwest to southeast and the other one an unknown one going northeast to southwest, so just like ridge crest.
Right.
So I thought that was interesting. So, and the fault it was actually on was what's called the Oceanic Fault, and it's part of the mountains there. So I don't even know if the Oceanic Fault is marked on our big map or not, whether it is or not.
I'm not sure, bud. I know this it's off Lompoc, so I don't see it out here.
Yeah, just like the San Simeon Fault is the bottom of the hill, and the Oceanic Fault is like the top of the hill. But I don't even know if they even have it on there.
Right. Here's the San Lucia Bank Fault here.
Yeah,
and then here's a Hosgary.
Yeah, San Simeon Fault is like the bottom of the hills, because he said that in the presentation. He was super detailed, and like the Oceanic Fault is at the top of the hills, whatever the hills are called. But I don't see it on there.
There's Nacimiento Fault. Here's San Simeon right here.
Yeah. Yeah, Oceanic Fault. Yeah, it is on there.
Yeah, there's the Oceanic, which goes north. It looks like that one is the West Wasana Fault in the Santa Maria River, and Little Pine. It looks like a splay off of the either the Santa Ynez Fault or the Big Pine that reaches all the way out into the Santa
talk
Maria
about
River.
Little Pine and that other one coming up. That's the top of the Santa Maria.
Yeah. All these tentacles are related, and so when if there's an earthquake up here, they'll feel it up in here because they're all combined. They all kind of like
But
connected
that
to one another.
presentation was an hour long, so it was super detailed. At the end, the engineer guy that was responsible for retrofitting all the buildings was on there, and he explained how they fixed them and moved them all back into place, what ones they had to
Right.
fix. So
Maybe
it
we'll
was-
watch that one after this presentation we got going on here. That'll
yeah, because
help
it was
us
like an
understand.
hour long, super detailed. And
Right.
the USGS guy explained the difference between the thrust faults and the strike slip faults, and he went into super detail on everything and explained it all, and used all their newest stuff they have on it. He even used their magnetic gravity stuff from the satellites.
Oh,
Showed that in
oh, wow, that's really interesting, isn't it?
they can see like what happened after the quake, like how it moved. So he was explaining all that.
Mm.
And then he showed like the ones they have now where it shows like where the quake was and then all the aftershocks, and then he show which fault it was on and which unnamed one it was on. So it's similar to the stuff that I've looked at for Ridgecrest. But see, it's because it's all the newer stuff, so they're adding more detail to it.
Right.
Stuff. And he said in his presentation, his part of it, whatever he did, 15 minutes, because they try to keep their presentations to an hour. He was trying to use the most simplified version to describe what was going on, he said. So he condensed it all down to explain like what happened with that quake. So it's pretty good. So we can watch that one after, but
yeah,
because it had a lot of events.
Right on.
But anyway, so back to the faults. So we talked about Hosgri there first, and we got to do the top one because now they refer to it as all like one big fault zone. So they're combining it all together. Like when the San Simeon quake happened in 2003, they were calling this the Hosgri San Simeon San
Right.
Gregorio fault zone. But since then, because there's so many offshoot faults to it, they're just calling the whole thing now San Gregorio Hosgri fault zone. So it basically goes from north of San Fran all the way to Lompoc. So like when you're looking on our big map here, you're seeing all these little faults and splays and all that, but now trying to simplify it all down. And that's so all the studies now either are referring to the Hosgri section or the San Gregorio section. That's what they're doing. So they're trying, they're trying to figure out the slip rates on everything and when they had quakes before and all that stuff. So that's what they're working on right now. And so now we'll talk about the second section because you read the first part that was Hosgri part. Yeah, so we'll do San Gregorio next, and then I'll show you a couple of the newer studies from 2018 and one from 2023.
All right, so do we know what kind of, I know it's probably on the SCDE or whatever those guys are.
Well, right now, based upon the newest study, they think it's both a strike slip and thrust both.
Okay.
The newest study in 2023 says all these other faults that are in there that are the northwest to southeast ones and the ones that are cutting across to it, they're all part of the same thing because it's what's lifting up the coastal range. That's what it says in the newest one based upon all the stuff they've been doing. So it's important that we understand that these strike slip faults, some of them have the thrust fault component with them as well, and that's what they're finding.
And that's what I'm trying to find.
And the USGS talks about that in his presentation too, right at the end.
Yeah.
Because he basically said everybody focuses on the strike slips, but the thrust faults are just as dangerous, and that's what he says at the end of his little blurb. Because he explains like the difference between thrust faults and strike slip and all that. And he has all the diagrams, and then he explains the beach balls and all this stuff when you see
Right.
him.
That'll be an interesting presentation. Cool.
Yeah, and it's all like a PowerPoint, so it's all like right
Mm.
in the
Right.
thing, because it's done by the California Earthquake Authority, and they do all like a bunch of historical quakes, and they usually do it like on a anniversary of it. So San Simeon was 2003, so they did it last year because it was a 20-year anniversary. So they went into super detail. So they had the USGS guy there that they analyzed all the stuff, and then they had the fire chief and the guy that retrofitted all the buildings and checked the damage. He was the engineer. So it's like crazy stuff. And they were making it like condensing it down so it could all be in an hour. Like they probably each could have done like an hour presentation, just each one of them. But for this thing for the California Earthquake Authority, they condense it all down into like an hour.
Yeah.
So,
Well, my problem with all of this is determining what's the hanging wall, what's the foot wall. Very difficult for me to figure out. I think it might be the fact of the
well, it's hard for them to figure out too if you read the studies, because that's
yeah.
what they're talking about in them, right? Because they know that the coastal range is lifting up, right?
Yeah.
But what they're trying to figure out is how, like when the quake happens inland on shore, it's still somehow related to the faults that are offshore as well. So even though it's lifting up in where the mountains or hills are, or the range, whatever you want to call it, it's still because of how it's all connected to the ones off the coast, and it's all adjusting to what the San Andreas is doing too, because it's all part of the same system, which it gets into detail when we talk about the new studies. So we'll get there when we get there.
Right.
Yeah, because they explain like why it's doing that there in comparison to the LA basin and the transverse ranges and all that once we get into it. But we got to read about San Gregorio before we get into the studies. So we'll do that next. So the San Gregorio Fault. The San Gregorio Fault is an active 209 kilometer on a 130 mile long fault located off the coast of Northern California. The southern end of the fault is in the Pacific Ocean just south of Monterey Bay, and the northern end is about 20 kilometers northwest of San Francisco, near Bolinas Bay, or Bolinas, I don't know how they say it, where the San Gregorio intersects the San Andreas Fault. Most of the San Gregorio fault trace is located offshore beneath the waters of Monterey Bay, Half Moon Bay, and the Pacific Ocean, though it cuts across land near Point Ano Nuevo and Pillar Point. The San Gregorio Fault is part of a system of coastal faults which run roughly parallel to the San Andreas. The movement of San Gregorio is right lateral strike slip, and the slip rate is estimated to be 4 to 10 millimeters per year, 0.2 to 0.4 inches a year. The most recent major earthquake along the fault had an estimated magnitude of 7 to 7.25 and occurred after 1270 AD, the earliest calibrated radiocarbon date for a native California cooking earth at the Seal Cove site near Moss Beach that shows signs of displacement. So this is like based upon their other studies that they've done. So this quake happened after 1270, but before 1775, when Spanish missionaries arrived in Northern California and recorded history began for the region. portions of the fault come ashore near the cliffs between Pillar Point and Moss Beach are sometimes referred to as Seal Cove Fault in the geological literature. So that's what they called it before they named it San Gregorio or whatever. So, and then that's chart over on the side that's in the Wikipedia article, which I've seen in other ones before. It talks about the probabilities of a larger quake on all these faults, and it has like a percentage thing on it. So I thought that was interesting. So they have only a 10% chance on the San Gregorio fault right now.
San Gregorio is only 10% chance? Okay. Gregario, right?
Yeah.
Okay.
So together, they're both like 400 and whatever it is, 420 kilometers long if you put both Osprey in. So Osprey goes from long Lompoc right to Monterey Bay, and then San Gregorio goes from Monterey Bay to just a little bit north of San Francisco, where it runs back into the San Andreas again. So it's kind of like an offshoot of the San Andreas.
All right. So I was just drawing the difference between a reverse thrust and a what do you call it? A thrust, a reverse and a thrust, and a normal fault and a right lateral. Right lateral is the left-hand side is moving away from you, and the right-hand side is moving towards you. San Andreas is a right lateral strike slip. So that's, and what the thrust fault is due to, because it's not a straight up and down. It's let me see, did I do that wrong? I think I did. Anyway, it's man, I just messed that up real good. Let me see if I can share with you what I'm showing. So share screen. It helps to know what kind of fault we're working with here. Show on stream. There we go. So I have 3 images here. The red line is the faults, and the reverse and thrust fault is, this is the hanging wall, which is to the right. Let me remove that. That might be helpful for you. So this portion of the ground on this one rises up over the footwall. The footwall is always on the right in this scenario. And when it's a normal fault, the hanging wall falls below the footwall. All right. Often I read online where they're talking about 4 different kinds of faults, 3 different kinds of faults. And it's pretty difficult for me to keep a line of it. We have tectonic earthquakes, convergent boundaries, divergent boundaries, transform boundaries, volcanic earthquakes, collapse earthquakes, induced earthquakes, artificial earthquakes. Each of these have their own kind of characteristics. So they're different kinds of earthquakes. But what's going on in the earthquake? And I think if we understand how these earthquakes and what they're doing with the content we have tonight for you, it helps you understand the movement of the San Andreas, i.e. the Pacific Plate and the North American Plate, and their relationship And the right lateral, which is on the bottom, the arrows are moving this way. The left-hand side is moving north. The right-hand side is moving south. That's a right lateral. If it was a left lateral, the right side would be moving north and the left side would be moving south in this image. So there's the reverse faults is the hanging wall rises up over, which is a thrust fault, and the normal is where the hanging wall drops down, and the faults the footwall rise is up. So these three kinds of faults are really kind of interesting. We can go into the depths of all these. That the normal faults are the most common fault, where rocks above the fault plane move down relative to the rocks below. Normal faults are often found along divergent plate boundaries, such as under the ocean. Reverse faults, the opposite of a normal fault, where the rocks right above the fault plane move up relatively to the rocks below. Reverse faults often form along convergent plate boundaries. A reverse fault with a small dip angle, there's the angle, not straight up and down now, is called a thrust fault. A strike slip fault, also known as a lateral faults, these faults form when the rocks on either side of the nearly vertical fault plane move horizontally. Strike slip faults are described as right lateral and left lateral, depending on which way the movement goes. And understanding these differences is key to kind of developing an image of what's going on here on these fault systems that we're working with out here. Right now, we're talking about the Haasgari fault or Haasgari fault. I added an A in there. Apologize. And here's the San Simeon right here. These faults are happening because the North American plate is here and the Pacific plate's here. The Pacific plate's moving north, northwest, and it's running into parts of the and receiving tension from North America because they're converting or convergent, right? They're coming together. And as they do, what we're going to notice here as I go back and show you my screen again, we have several of these faults that are offshore, and we have the San Andreas out here. And there's more than, I'm just kind of drawing real fast here, okay? What you'll notice that as these faults are going, these are on a side view, these are the pizza boxes, right? So this is the side view. So file new again, don't save it. So as the North American plate is crunching into the Pacific plate, right? The Pacific plate's moving so fast, it's making these it's not flat, right? No, you got parts of it are rising up like this. And that's how we get our mountains in the past, in the backgrounds too, because of where the fault system, the San Andreas is, and the way this is all moving to north and this is moving south, yet they're still converging. And as they do, we're catching a fault here, and a fault here, as well as other faults that break on these. And some of these are hidden thrust faults. It means they're down in this section and we don't see the top part. It hasn't, the ground or the mountain hasn't eroded yet, or the land hasn't eroded for us to see it. And we call those blind thrust faults. And so this is what's going on off in the west on the Pacific side. Here's the San Andreas. Remember that, right? San Andreas goes all the way down below. These ones are being, as the plate slides, it gets bound up on each other. So, and That's how mountain building happens. And it lifts itself up and it creates these thrust faults. And so each pizza box, if I understand it correctly, right, each pizza box has that, it rises up over the other one. So the hanging wall is out here. The hanging wall is out here. The hanging wall is out here. Or no, the hanging wall's in the front. The foot wall is dropping down behind. So it's rising up over the foot wall. And, you know, and in blind thrust to say it all happens underground, you don't see it. So I think that helps us kind of understand what's going on here with these systems. These are right lateral moving north. The other side's moving south. And, or actually it's just moving slower than what's the outside is. We have 1, 2, 3, 4 main areas. And so this one's lifting over this one. This one's lifting over this one. And this one's lifting over that one. So at the base of the dirt here, or the landmass, one's rising up over the other and rising up over the other. And so we have stuff that winds up coming out of the water and creating all these coastal plains, because the convergence of the North American plate and the Pacific plate crashing up against each other. And as the Pacific plate moves north, northwest, it's breaking and it crumbling. Like you take two cookies and push them together dead on, it's just going to go straight up. But this is not happening. One's kind of coming a little bit south, one's kind of going a little bit north. And so it's like almost where it's going to slide by each other, but parts of it break off, and it gives you these funky little bends in the faults, and that's what the transverse faults all right here, you know, in the greater Santa Barbara and Ventura, Oxnard area, and Santa Maria, and then San Simeon, and then up here Fort Hunter and all this, and then we have the Monterey Bay. That's how all these things are working. And what we're doing is we're trying to tell you, or trying to explain to you, that all these major faults are related to the working of the San Andreas. And there's a percentage of these faults out here that, let's say, it 100%, if the San Andreas made all the earthquakes on the San Andreas, then none of these faults would exist. But because these faults do exist, and it's fact that this can't slide, these ones slide first because the weakness out here. And they take, you know, 30, 40% of all the power out of the sliding of the San Andreas. And then the other side takes another percentage. So it's like 30 or 40, 30, and maybe 20 or 40, just the San Andreas. So in looking at the whole system as a whole, you can see that how these faults interact with each other. And that's what we're telling you, and that's why we bring it up, previous earthquakes, and how these earthquakes relate to one another, and how they relate to the whole San Andreas fault system and what's happening here in California. I hope that kind of brings it all together for you. Do you have anything to add to that there, Canuck?
No, because we're just going to do the first study article, the simple version that the USGS did that explains what we're talking about. So
the structural analysis, San Simeon?
Yeah, the one that says bend in an offshore fault helps shape the rugged terrain of California.
Okay, I got you right here. All right, share this tab. Go right ahead, bud.
Yeah, so I'll just read it. And we're going to go into the map after the map.
Do you want me to read it? You want to read it?
Doesn't matter. You can read it. I can read it. It's not very
long. Go ahead,
long.
buddy. Go ahead.
Yeah. Okay, so this article is part of the August 2018 issue of the Sound Waves newsletter. So this is based upon the study that came out in 2018. So a 65-mile long stretch, the Big Sore Bend, of a long fault offshore of Central California plays a major role in shaping the steep topography of the state's Big Sore coast. A new report from the USGS published last May in the journal Tectonics explains this role. It also describes findings with implications for earthquake hazards the fault could trigger, including shaking, coastal landslides, and tsunamis. The San Gregorio Hosgri Fault extends along the central California coast for about 250 miles. For most of its length, the fault lies beneath the Pacific Ocean, which is one reason why it is not so well known as its inland cousin, the San Andreas Fault. Both faults are part of a broad zone separating the Pacific Plate on the west from the North American continent on the east. Like the San Andreas, the San Gregorio Hosgri Fault is right lateral. To an observer on one side of the fault, the other side would appear to move horizontally to the right. In 2011, USGS scientists led by Sam Johnson mapped a poorly known stretch of the San Gregorio Hosgri Fault offshore of the Big Sur coast between Piedras Blancas and Point Sur. They used high resolution tools to record seafloor depths, image sediment layers under the seafloor, and measure the amount of magnetic minerals in sub-seafloor rocks. Features they observed on and beneath the seafloor show that the fault slips vertically as well as horizontally in this region. The landward side of the fault here moves upward by about 3/100ths of an inch per year, as well as horizontally to the southeast by about 1/10 of an inch per year. The vertical motion results from rocks on either side of the fault pushing against one another as well as sliding past. So it's doing both. The USGS scientists combined their 2011 results with data collected previously for the California Seafloor Mapping Program. They saw that the stretch of the fault they were investigating offshore Big Sur forms a large bend between more northerly trending parts of the fault zone to the north and south. They named this stretch the Big Sur Bend. Compressional force along the Big Sur Bend has helped push up the rugged Santa Lucia Range. The coast in this region has a narrower continental shelf, steeper terrain, and more frequent landslides than coastal areas to the north and south. The 2011 mapping showed that the San Gregorio Hosgri Fault is continuous for at least 140 miles, and a major earthquake could potentially rupture that entire length. Such a rupture could generate a magnitude 7.8 earthquake, although scientists note that no data exists to indicate whether such large earthquakes have occurred. The largest historical earthquake attributed to the San Gregorio Hosgri Fault was a 1926 magnitude 6.3 quake in central Monterey Bay. The largest earthquake on the fault in the Big Sur Bend area was a magnitude 6.2 event in 1952. So I thought that was interesting when I read that.
Oh, yeah, 1952, yeah.
Was the same year as the Tehachapi quake.
Tehachapi, yeah.
Yeah. So earthquakes of such magnitude can trigger landslides, a major concern along the Big Sur coast, where winter rains already produce slope failures that periodically close the popular state Highway 1. Large destructive landslides along the steep front of the Santa Lucia Range are common, note the authors of the report, and strong ground motions from large earthquakes will push many slopes beyond their stability thresholds. Citing another danger, they write, submarine landslides along the steep shelf break and on the flanks of the incised submarine canyons have the potential to generate small tsunamis. And then it says, read the new report for detailed pictures of factors that make Big Sur coast both beautiful and hazardous. And then they have a big picture of the landslide that happened there in 2017 about how it's blocking the highway. It's gigantic.
Yeah, it's a pretty good landslide there. Piedras Blancas is down in the south. That's that little finger that's down there. Um, and a lot of this is underwater. So this is a pretty good article. I'm going to save this article for you. Research, and I'm gonna see if I can download it PDF.
And then the next one is the actual map that's in there.
Right.
I sent you that one so you can make it bigger.
Right. I've got a couple of the. I got the PDF of the new article. I'm trying to download it though. Wonder why it won't let me download.
Yeah, it's super detailed though.
Yeah. When it goes off, it tells us about it because it is offshore. This fault is offshore, and due to what did it say? Because the land above the water is so steep, parts of it fall off into the ocean, and that's what we're seeing here.
Yeah.
In this image right here. Pretty serious landslide. The Big Sur is, I've been up that way, and it's pretty incredible.
Interesting. So on that one map, they show basically the whole thing.
Right,
so I like to put it all on one map.
Right. Shelf break, Big Sur Basin down here. I'm sure this tab instead. There you go. So I went out there and pulled up the article on its PDF, and you can see Sur Basin, and there's the fault system here. I'm assuming that the shelf break 97 meters up here, the fault bounded ridge. Yeah, they're looking at. I think that was your
watching something downstairs. Yeah, she's watching some movie or something.
Sandy, what? Something got her going. Yeah, there's a lot of great images here. I'm going to put this in chat for everybody. You want to look at this on Twitch there, but I'll try to put this in the information for you in the when you're over on. Yeah, this is really cool. Great. All right, so backing out, going back to where you're talking. So what is your conclusion from what this told you about the Big Bend faults and the San Gregorio Hosgri fault? What did it really speak to you about?
They're kind of suggesting in there that it's doing both things in 2018. So
doing both what?
So it's both right lateral, but it's also thrusting too. So that's what
right.
Saying.
Yep.
It's doing both. And then in 2023, which that's one we haven't looked at yet. They go into more detail on that because they're trying to figure out like what it's slipping at and all that, which is what all the new studies are trying to do.
Are they looking for the rate of slippage, or what do you mean by trying to find what?
Yeah, they're trying to figure out how fast it's slipping, so then they can use that to figure out.
Right. In the picture you have on your screen, the northern section of it, that's San Francisco Bay, and San Jose is right here, and the San Andreas kind of comes up through here. The Hosgri, San Gregorio Fault, Big Sur Bend, and Gregorio, not Gorgonio, Gregorio. Santa Cruz is right here, and Monterey Bay, and it goes south of that. So in looking at this, what we're looking at is this orange right here. And if it comes up, it's Seal Cove Fault, San Gregorio Fault Zone. Remember what we did in Southern California? We talked about fault zones. And the fault zone is made up of several different faults. And just like this one, the San Gregorio fault is made up of several faults. The San Gregorio fault zone, we can zoom in. We see the Seal Cove fault just off here at San Mateo on the backside, right? It goes all the way into where there's the the Golden Gate right through here, and it comes back to the San Andreas where Point Reyes actually comes into that area as well. North of it, we're not talking about that tonight, but we're really trying to see this Seal Cove fault. I don't know what this one here, unnamed, yeah, it's part of it. So the extent, even the Point Reyes fault, it has a splay off of that Seal Cove fault, which then turns into, again, the San Gregorio. And then just north of Santa Cruz and the Cabrillo Highway here, you'll see a Botano fault. Yeah, I lived up in here. Ben Lomond, I lived up in here. Boulder Creek, yeah, up in this area. I lived up in there, Kings Creek, all that stuff up in Ben Lomond, Brookdale, and in Santa Cruz down here. That's the Ben Lomond fault, part of this whole fault system. The Ascension fault is a little bit west of this San Gregorio fault, but you see it does have a subduction component to it, just like out here does too. Several subduction zones, paleo subduction zones, maybe the old ones, right? Monterey Canyon comes out here. Major Canyon, that's a huge canyon. Comes off of Monterey. I think it's the largest in the West Coast, to tell you the truth, at least in California. The Monterey Bay fault zone is another splay off the San Gregorio fault zone. And the Palo, Colorado fault zone is another one. And here's the Sur, Big Sur fault zone. And all of it just continues down right into the Hosgri fault system down in the south in San Simeon. So in the north, we have the Seal Cove, San Gregorio, right? Turns into the Palo, Colorado, then the Big Sur. And then from there, it goes all the way into the Hosgri fault, turns then into the San Simeon fault zone and part of the same Hosgri fault zone. And it continues south into Lompoc. And that's why if this whole thing broke, there's a possibility between 7 and 7.8 if the whole thing ripped. Now, many people talk about the rips, in my mind, talking about the rip up in the Pacific Northwest. Oh, yeah, it's going to rip from California all the way up to Canada. Okay. Instead of, I don't think we have any modern day evidence of that ever happening. We got the 1700 one and they say, oh, yeah, it ripped around the same time. But we really don't have any evidence of that. And in my mind, I would see, this one rips. Then, minutes to days later, this one rips. Minutes to days later, this one rips. Minutes to days later, this rips. And we see this all the time happening in all of our studies, where if we just follow earthquakes from the south, they kind of generate going north because that's the direction of the plate. Now, sometimes it looks like it goes south. It starts to the north and moves south, but it's really because the plate's moving north. So I find that interesting as well. Do you have anything you want to add to that, Canuck?
No, I'm just going to go to the next one.
Okay.
Yeah. Which there, in this next one we're going to look at, I'm not going to go into super detail. I'm just going to read like the abstract part. because it gets in super technical, but we'll just.
Yeah, it didn't come up for me. I don't know why.
Oh, well, here. Put it in again. Little copy.
Hosgri. The Hosgri fault transpressional slip?
Yeah, that's the one.
Okay, I got it.
Yeah. So I'll just read the abstract part of it.
Okay, bud.
Yeah. Coastal uplift is a common feature of Pacific Rim tectonic deformation. The 1989 magnitude 7.0 Loma Prieta earthquake illustrated that reverse oblique slip on a transpressive segment of the predominantly horizontal slip San Andreas transform fault produces coastal uplift. Now, to put that in simple English, it's a thrust fault again. Because if you read about Loma Prieta, they say it had the thrust fault component. If you read on all these newer earthquakes, they're always saying now they had a thrust fault component. So in this thing here, that's what they're talking about at the first. So they're saying a lot of these recent earthquakes that everybody knows about or that focuses on have a thrust fault component. And you'll find if you look up the ones in Taiwan or Japan or whatever, it's the same thing. They're all thrust fault related. So they're all showing up as thrust fault stuff, even though they're right lateral or whatever. So that's what they're arguing in this. And they're trying to figure out the Hosgri section mainly. And I'll read more of it here and they'll explain what they're trying to do. So in west central California, the 400-kilometer long San Gregorio Hosgri coastal fault system of near vertical to steeply northeast dipping, reverse oblique, dextral strike slip faults also contribute to coastal uplift. Published southern Hosgri fault dextral slip rates are close to 4 times reverse rates. Viscoelastic deformation modeling using published transpressional slip rates along the southern Hosgri fault reproduces observed emergent marine terrace uplift rates, offshore Hosgri fault deformation morphology, and crustal structure from San Luis Obispo Bay to Estero Bay. Our coastal uplift rate modeling is constrained by a unique combination of measurements. Offshore reverse and strike slip Hosgri fault zone slip rates and greater than or equal to 125 Ka, so that's 1,000 years. Onshore emergent terrace uplift rates and adjacent to the HFC. The previous proposed conceptual rigid block models of southern central California coast, CCC, so that's what they're calling this section, CCC, Central California coast, invoke local onshore thrust or reverse faults to explain coastal uplift. Observed transpressional offshore Hosgri fault deformation rates alone rigorously reproduce observed coastal uplift rates and crustal structure along the southern CCC. So now I'm not going to go into this in super detail, but they're arguing that the offshore fault is what's doing the uplift of all the faults that are onshore. That's what they're arguing in this new one from 2023.
All right.
Because of how and the angle it's at, and based upon all the stuff they've added to the offshore stuff recently, because now they know how it goes down in there and the angle it's at and how it connects to the hills that are being risen up and all that stuff. So this one is going into even more detail than the 2018 one because we have more stuff we can actually use now to see all these things. Because see, it has a section on crustal structure and neotectonics, and it's talking about how it goes down in and which side is actually the hanging wall and all that stuff. Like it's going into like into super detail on everything, and like how far it goes down in, like 10 to 15 kilometers down into the crust and stuff that's at 6 kilometers. So it's like going super crazy, wild detail in it, which I don't want to get into super detail, but basically what they're saying is this fault system, the big one, San Gregorio Osprey Falls, is what's actually doing the coastal range uplift. And when they get down to the end of this, which they're focusing for this one in the mainly on the Osprey section, so this other section, they're saying, which is funny when I read through all of it, they're saying that they think it's going between 10 and 14 millimeters a year, which I thought was funny because that's the same as what all the borderland faults are doing. Which I don't know. If you read the new stuff on them, they're saying the same thing. So it's slipping at the same rate as the borderland faults are, which I don't know if they're even, whoever's doing this study, if they looked at the borderland ones to see that. So basically it's moving the same as the borderland ones down in southern off the coast. So I thought that was interesting. So that was my conclusion after reading all through this crazy gibberish that they got in here. Because it just gets nuts after a while, because they're talking about like the formulas they use to figure all this out. And
right.
Yeah, and that's what they're doing. But I just find it funny because like the farther you go back with these, like if you went back into the like late 90s, early 2000s, because of the San Simeon quake, they were including the San Simeon fault as part of the whole fault system. And then now that they've gone deeper into it, they're trying to figure out what's causing all the stuff on shore. Because they're trying to figure out why are all these mystery faults showing up with thrusting on them, like way inland where they don't know where there's a fault, but it's doing
what's pushing them is basically what they're asking.
That's what they're trying to figure out. So
right.
They're trying to figure out what fault is controlling all this for it to make a random quake in on the hills or the mountains or the range that they didn't know about before until it happened. And then they say they're all thrust faults because they can't see them, right? Because before they didn't know how these ones offshore are connecting with the ones onshore. But they can do that now because of all our modern stuff that we're using, whether it's bathymetry or satellite or whatever. So they're seeing how all this stuff is connected, like how they all connect like down farther in the crust. So they're crossing over each other and at different angles. And
yeah, it sounds to me like the point of the article is to say, hey, look, everybody, we all thought that these were strike slips. They have a strike slip component. Rather, these are thrust faults. And the strike slip component is that it's all moving northwest, but they're also folding over one another. And when they study them, they're finding a blind thrust on the backside of every hill that's made. And on the foreground of the hill, it's like the front end of the top end of the pizza box pushed up on the next one, which pushes up on the next, which pushes up on the next. And then as you go further in the depths of the dirt, so to speak, you get you know, I'm drawing a picture so you can see here. I'm gonna share it with you now because I was listening to what you had to say. I think this is an interesting article, And with what we said the other day, or earlier today, I should say, um, I think it's pretty incredible. So basically, the basements of all of these thrusts, I got to put up the San Andreas. I apologize. San Andreas is up here. These are the coastal mountain ranges that are building up, and then we have the ocean is right through here, right? So it's all waves, right? All these are waves. So under the ocean, we still have these thrust faults pushing up on one another. These red lines in the middle here and here, these are the faults themselves. But as the basement, like this fault up here would be probably this sideways looking, right? And then the next one, and then the next one, and the next one. So they all share the same underlying bedrock as they come ashore. And what that suggests, I don't know how deep, did you see any kind of depth to it? Let's say from here
Yeah,
down.
One of them said, I can't remember which one it was down 15 kilometers. And then another one was intersecting it at 6 kilometers. I can't remember which ones it were.
So the bedrock, if we were to flip this on its ear, the bedrock's like this. And this I just drew straight up and down to try to give you a depth perspective. This is higher in altitude than down here, of course. This is sea level. This is higher. And so you have one mountain range, another mountain range, another mountain range. This is very simplistic. Now, depending on which way the thrust's going and the strike slip's going, this could be this direction or this direction. Okay. So what I'm trying to get at is the basement of this rock is down here. The basement of this rock is down here. The basement of this rock is down here. And this one is down here. And this one is down here. But they all are one big piece, because I think the San Andreas goes 25 to 50 kilometers down. That's all the way through the crust. The San Andreas is completely through the crust. The edge of the crust from right here all the way down, let's say it's 25. What they're saying is the one that's interiorly could be like 20. The next one, 15. The next one, 10. The next one, 5, right? So all of these are sharing the same bedrock together as it moves ashore and crumples because of the rate of the San Andreas, which is moving a lot faster than North America is coming in. And it's sliding and pushing up on each other, because out in the ocean, the San Andreas, or not, the Pacific Ocean's moving north at a huge clip, 65 millimeters a year, right? A huge clip, it's like 7.5 millimeter or 7.5 inches a year. But the San Andreas is only moving, 2.5. So as it's slowed, because it's converging in on North America, that's where the mountains are building up in each other. It's like it's buckling, right? Because they're coming into contact, and the edge of it's moving so fast. The other one's moving so slow. They're not moving at the same angle, but they're almost one's moving, north out. The other one's kind of moving just a little bit south, but it's grinding, and it's taking all of this taking all of this and rotating it up this way and building up. It builds upward. And because the San Andreas is moving in that direction, and the North American plate's kind of moving in that direction, not due south, but southwest, at the edge of where the Pacific, the San Andreas is. And that's only an illusion, because the Pacific is moving so fast. It's faster than the North American plate which is moving supposedly due west, right? But it looks like it's moving, southwest, or southwest. but it's only because the speed of the Pacific moving north. It's an optical illusion. But because it's moving us up, it's hitting the North American side in convergence, and it's moving so fast. It's building the coastal ranges on top of each other, and then and that's all that exterior. So if we were to look at a map on the USGS here, and I'll share this instead, and terrain. All right, so I zoom in here, and our area of discussion is right down here. This is the San Andreas. Everything west of the San Andreas is the Pacific Plate. But we have these mountains here, right? The Santa Lucia Range. Well, how the hell did they get there? That's this building up, this overlapping that we're talking about. This stuff begins out to sea. And that's what he's talking about, the Hasgari Fault, which goes all the way to San Luis Obispo, all the way up. And then the other one, which goes all the way into San Francisco up here. So all of these mountain ranges are made this by the uplift of the Pacific Plate crashing against the North American plate because it's moving so darn fast. It's 65 millimeters here, but out here it's 100. So it's moving really fast relative to how the Earth moves, okay? For us, it's not moving fast, but for them, because it's massive. And it's what's creating all of these mountain ranges, these coastal ranges, because of that movement. And these coastal ranges are due to uplift. Like with Canuck and I, we talked this morning. San Francisco's being uplifted, you know, all the way to Santa Cruz Mountains. That's all by uplift. Now you can see different, motions and where all these are breaking apart. A lot of it's erosion, a lot of it's, rivers running through it and eroding it. And also the way a weakness in the plate can make a splay, the rise and fall of the water levels, storms, and all of that, all playing a role of shaping the edges of the plate. But we saw in California, when we first started, we were talking about down here in the Palo Verdes area. There's a section of Palo Verdes right here that's falling into the ocean, but it's not really falling. What's happened is it's I'm going to draw it on a map, and I'll show you in a minute.
Well, that local guy that was on the beach there, the real estate guy, said that it's just coming up out of the water.
That's what I'm about to show you. Yeah.
Yeah. He said the hill's falling down, but he said the beach is coming up out of the water. He said the beach is getting higher. There's more beach.
Right.
So to me, that would make sense if the whole thing is a thrust fault.
Correct. And that's kind of what we're trying to. Oh, I already showed it to you. You see it. I didn't know. Yeah, you can see it. So the land is falling down the coast, but because it's falling down, it's hitting the bottom, and it's building up. And so parts of it's coming out of the water.
Yeah, and he's saying the beach goes out way farther, and there's rocks.
Yeah.
If you watch the video.
Right, and it's all rock.
Yeah, he's showing like where the slide part is sliding down, but then he's down on the beach. He said the slide's not here, but he said all this has come up out of the water the last, I forget how many years he said, like the last 2 or 3 years. He said
2 or 3 years, yeah.
Way farther. So I said, well, that's friggin' weird.
Yeah,
I said,
and this kind of what sparked our interest about doing all these things, because like, hey, wait a minute, what is going on? And I think now with the studies we've done on, I don't know, probably 20 episodes now, we're beginning to understand how the Pacific Plate grinds up against North America and what's happening and why these quakes are happening and what kind of faults are out there. Once we learn what kind of faults, we know what's going on. This is the uplift is here and it's doing that there. And what it does, there are people here that'll just listen to say, okay, all this stuff is blah, 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 whatever. I don't care. All I want to know is when the next earthquake's happening. Well, that's not what we're doing here. That's not what we do. We're learning about how the system works. And this is only a microcosm of the entire planet. We're only looking at one little 800-mile section right now. Right now, I think we're looking at a 240-mile section, Central California. But this is what's going on. It explains the coastal ranges. It explains the mountain making in the San Gabriel Mountains, which is on the eastern side of the San Andreas, right? It explains all of these different systems that we're dealing with. I think I'm where this one here. Share this. I am sharing it. Good. It's the San Gabriel Mountains. It explains that. It explains the Malibu Mountains. It explains the Topatapa Mountains, the Sierra Madre Mountains, San Rafael Range, the Santa Ynez Mountains. They explain all these are thrust, and you can kind of see it. They're not like straight across. They're kind of northwest to southeast kind of shape as it goes on here, Lompoc. And you can see these mountains side by side, right? That's because they're made from thrusts. One is coming up over the other. As one's rising up, the underbelly is rising the other ones up. Why? Because they're running right here against the San Andreas.
Like years ago, they didn't care about this, right? They were just,
right.
Well, there was an earthquake. But now they're getting into try and figure out how it's all working. And they're going in super detail now because we can do that with the technology that we have. But to me, it's always worked the same way. It's just they're figuring out how it works now, which you still should be able to do what I'm doing, go back and figure out where the quake came from, because it should work the same way.
Yeah, Kat, we're going to get into the Wasatch Fault after we go to the north, then we're going to go east.
Once we get to Utah.
So we are going to do that. You're ahead of the game, and so but in context today, to try to keep the picture going, we're speaking specifically on how these coastal mountains are made, and what these thrust faults are doing.
Because that's how the mountains get there. Like if you read the new stuff on the New Jersey quake that happened earlier this year, they say it's a new thrust fault that they didn't know about on the East Coast that goes the same way as Ramapo Fault. So northeast to southwest. So it's not Ramapo Fault, but it's another one that's right beside it. And now they say it's a thrust fault. So here's the same thing again. So it doesn't matter West Coast, East Coast, middle of the country, wherever you got a hill, there's a possible thrust fault because that's how the hill got there. If you want to simplify this right down, like to make it as simple as possible. If you got a hill, chances are it's related to a thrust fault, or you got an ancient volcano in your backyard, but it doesn't matter. It's the same thing. And probably Nick's going to find the same thing when he starts going into all this stuff about the volcanoes.
Yeah. And that's what he's talking about, the basement stuff coming to the surface, and
because all that stuff is pushed up. So he's calling inliers and outliers and
right,
whatever you want to call it this week. It's still stuff that's all thrusted up that was down below before. That's all it is. Well, how did it get thrusted up there? Well, there had to be thrust faults lifting it all up. So that's how the basement got up in the sky. To simplify, I made a rhyme. So
that's so good. And again, it really makes sense that these thrust faults coming in and the pizza boxes that he spoke about, that it exposes the underbelly of all the mountains. He's not even talking about it's Nick Zentner, by the way, for those people out there listening. He has a live show on, right now it's on Sundays and on Wednesday afternoons, Sunday mornings, or Saturday mornings, right? What day is it? Is this Saturday or Sunday? Oh, Saturday. Saturday mornings, and then on Wednesday at about noon Pacific time. What he's talking about is the basement stuff, and that all these volcanoes and the Cascade volcanoes have burned their way through this basement it's part of the uplift and the subduction that's going on up there in the Pacific Northwest. We have some subduction that's off the coast, but nothing like with this line right here, this major subduction zone. And these Cascade volcanoes that go all the way through Oregon and through Washington and into California, that they burn through the stuff that has accreted or it's been pushed up on shore by North America and the South and the Pacific Plate, or not the Juan de Fuca, but the Farallon Plate, smashing against each other, which created out here these Rockies and stuff. And before it accreted, like Washington wasn't there. Parts of it, it's probably back here by Spokane. All this stuff came ashore and was what do you say? When we talk about subduction, and I'll share this.
And to simplify it even more,
right? This one's subducting, and this one's is up, right? This plate's going down, but as it does, parts of whatever this here is gets shaved off, and then the basement goes down below, and then after it heats up, the basement comes up, rises because it melts and comes up and through a volcano. So and we didn't make a volcano, right? So parts of it is, the top part shaved off, and the underbelly, or the stuff that's diving down underneath through heat, creates steam, and steam creates breakage in the rocks, and the gas and all that stuff tries to go to the surface, and it's heating up, and as it does, it creates magma, and then boom, comes through the surface. But parts of it is, if there's an island out here and this plate is moving this direction, it accretes this island. A big portion of it gets shoved up on shore, but the basement stuff gets pushed down, and then parts of it melts and comes up again on shore in through the volcano. So that's kind of what that means.
And that's why you get, when the volcano's having a fit, you get earthquakes.
Right.
But also when all these thrust faults are happening, when they're lifting everything up, you're getting a whole crap load of earthquakes too. Right?
Correct.
Because that's how it's actually moving it and lifting it up. So at some point, for all these big mountains to get where they are, they had to be lifted up by large earthquakes at one time, however long ago it was, whether it was last week or whenever. That's basically
Right.
what's happening.
Right. So I hope in context, what we're trying to do is just build a bigger picture for you to see how all these systems are working. I know when I started this stuff, really studying 5 years ago, well, almost 5 years ago, I didn't know anything. I'm still learning every day. Like I tell all my people on Joe Slick Live there on Twitch, I'm a learner. Just like y'all, I'm a learner. I learn something new every day. And it's like, wow, man. And sometimes they talk dates and it makes my head spin. It's like, what? I thought you said that over there. And then we learn that every year there's new technology, and there's new data. There's new people looking at the old data and going, wait, they kind of, they didn't apply this thing to it. So the data was an incomplete interpretation. And so they reinterpret it with the new data and the new technology today. And so that happens. Plus there's stuff that's still good, but we digress a little. Where are we at now, buddy?
Now we got to talk about the quakes, but we're only doing 2, so it shouldn't take
All
so
right.
long. Yeah.
The
so we're
2003 San Simeon quake.
Yeah.
Okay. Go ahead.
So I'm
It's
just
on the
going to read
screen.
the first part of this. I'm not going to go into super detail on the damage and all that, but
Okay.
cover the main parts of this. Yeah, the 2003 San Simeon earthquake struck at 11:15 Pacific Standard Time on December 22nd on the central coast of California, about 7 miles northeast of San Simeon, probably centered in the oceanic fault zone within the Santa Lucia Mountains. It was caused by thrust faulting, and the rupture propagated southeast from the hypocenter for 12 miles, 19 kilometers. The most violent ground movement was within 50 miles of the epicenter, though the earthquake was felt as far away as Los Angeles. With a moment magnitude of 6.6, it was the most destructive earthquake to hit the United States since the Northridge quake of 1994.
Which was a 6.7.
Yeah. No, I'm not going to go into big detail on all this damage stuff, because if you watch that video, if we watch that after, it explains
Right, we'll watch it afterward. Yeah.
how they fixed it. So,
Right.
and what they did and how it affected the building codes and all that stuff.
Right.
So I'm going to read the aftermath. Following the event, California enacted AB 2533, amending the California Business and Professions Code 8875.8, requiring that certain unreinforced masonry buildings that have not been seismically retrofitted have posted notice of the potential earthquake hazard. And the law was called Jenna's Bill after she was one of the people who died in this quake. And like the engineer guy explains all that stuff in this video that I watched earlier. It was an hour long. So
Right.
if we watch that, it's going to make
More sense.
Yeah.
Right.
Yeah. So the faulting, the area where the quake struck, displays a complex faulting geometry between the active oceanic fault and the older Nacimiento fault,
Right.
along with possible interaction from the Hosgri and San Simeon segments of the mainly offshore San Gregorio, San Simeon, Hosgri fault zone. So basically what we've mentioned already in the other studies. And the USGS guy talks about that in the video too. So anyway, so the next thing we're going to do is what we always do. We're going to look.
We're going to take some 2003. And I think we'll probably look at 2002, no?
Well, this one was right at the end.
Okay, so we'll use all 2003, yeah.
Yeah.
All right.
So we can go back into 2002 if we want, but
right. Well, for time Artid, we're already we're about an hour in. All right. Looking for anything Luzon, no, it's the Philippines, sorry. Coast of Oregon, January 6.3.
Yeah.
Oh. Didn't we just have a 6.5? On December 22. What was it? A 6.6, right?
Yeah.
All right. So Oregon popped with a 6.5, or say 6.3 first in January. Costa Guatemala popped with a 6.5. That's in the south. Colima popped with a 7.6. Oh. On January 21. Guatemala the same day, 6.5 in Guatemala and a 7.6 in Colima, Mexico. All right. Prince Edward's Islands, that's down in the Atlantic, right? In February, I don't know where these, it's not anywhere. Nothing in February. March.
Unimac Island Solutions, 6.6.
Okay, Unimac. Oh yeah, yeah. 6.6 up in the Aleutian Islands. So we have Oregon and Aleutians and Guatemala and Mexico. And then in March, we got the southern mid-Atlantic ridge. That's on the other side of the South America. Gulf of California popped with a 6.4. Wow. That's interesting right there. The Rat Islands started banging real hard, 7.1 to 6.2. Kamchatka had a 6.1. All right. April. The northern mid-Atlantic then popped 6.3. We've already talked about that earthquake. Again, remember when the Atlantic happens, something happens also, right? Panama popped with a 6.2. So sixes came up the mid-Atlantic, and then Panama pops. That's on the God bless America. It's a brain fart, man. Just you're like, hey, it ran out. Didn't want to be exposed. The Caribbean plate.
Yeah,
Excuse me.
North America.
Then we had Brazil, a 6.0. And then in May, we have wow. Oh, Colima again, a 6.1. That's Mexico.
Yeah, you missed there's another North Atlantic.
Oh, Prince Edwards.
North Atlantic, 6.7. Right above the Colima.
Okay, yeah, you're right. It didn't have a flag. That's why I missed it.
Yeah.
Yeah, 6.7. So 2 in the northern mid-Atlantics. Wow. Then Colima pops off, which again is north of the Caribbean plate in Mexico, moving up toward Baja California.
Yeah.
It's moving toward that direction. I don't know where Morro Gulf is.
Morro Gulf, Philippines.
Okay. June, Peru popped with a 6. Rat Islands again, 6.5. Kamchatka had a 6.9. Brazil again, a 7.1. Coquimbo, which is Chile, a 6.8. Wow. Then Rat Islands up at 6.9 again. And in July, Haida Gwaii, 6.0. All right. Moving on up again. Costa Jalisco, which is Colima area, again, 6.0. That's north of Colima, the next state. Then we go to August. I don't know where the Scotia Sea is. That's down in
that's bottom of
southern Atlantic. Yeah, the mid-Atlantic broke in the center and in the north twice, and now in the south by Sandwich Islands.
Yeah.
The Mockeries, which is underneath Australia.
Yeah, and see, look, here's our.
Oh, here's Greece. Wow. And there's Guatemala again, a 6.0 in Guatemala. The East Pacific rise, way down in the south. Pressure coming across at a 6.2. I don't know. All right, that's not us. So September, East Pacific rise again with a 6.1.
Yeah.
And
see, look what else.
Ascension Island again, which is in the middle of the Atlantic rift. There's the DR coming in with a 6.4.
Yeah, look at Hokkaido.
Hokkaido, bunch of Japan. Wow, big 8.3, 7.4, 6.0. That's no joke right there, boy. And Russia's been banging pretty hard. Russia got a 7.3 and a 6.4. Then there's another Russia up here too. What was it? Oh, Primavoy 6.2. So yeah, North Hokkaido again 6.5. So Hokkaido was going pretty crazy over there. Then we went into October. There's Siberia again. Russia, just that northeastern portion of the world from Hokkaido into Siberia and Kamchatka and all that just went ape turd. The Rat Islands were going ape. We had an earthquake down in Haida Gwaii. We had several earthquakes down there in Colima. We had a couple of quakes down in there in Guatemala. And we had several earthquakes up and down the Atlantic Ridge. Now we're having some earthquakes in the East Pacific Rise down in the south. And then we have a couple of good chilly quakes. And
Peru was acting up too.
And Honshu again, another 7 in a Honshu. God bless, man. And these poor people. Then in November, Columbia banks. So New Zealand again had a 6.4. So yeah, so Colombia popped with a 6.0 there in Colombia. Volcano Islands, Japan there. Rat Islands again, 7.8. Holy Toledo's. Gosh. Wow. And then Ostrovia again, 6.7. That's again north of Japan, right? Kamchatka, Siberia, Rat Islands.
West Virginia.
I didn't see Virginia. I'm not there yet. It's the next one. Virginia Commonwealth popped with a 4.5. That's how it works. The Atlantic moves North America, and we get interiorly in North America, something happens. I have to believe that the North Atlantic broke in 1812, and it went, or 1811, 1810, and it broke across the North America. And then the next year in 1812, California went off. So 1811 and 1812, right? So it wasn't done. Something broke out there in the Atlantic. I don't know if we can have evidence of within a year's time of a tsunami or not, but something big happened out there in the Atlantic that moved radically. I would have to say it was a real high magnitude earthquake out there in the Atlantic Ocean. Maybe several of them. It could have been the Rick James that was decided to go off with what it did a few years ago. It went like 25 fives or something. It was just really banging hard. So, and then we got Virginia. Now, that would suggest the mid to North Atlantic, because what was that quake? It happened in was it the 1800s? Off not Virginia, but South Carolina. That you traced across near, to the Mid Atlantic, and
1886. Yeah.
What the 1880?
1886. Charleston was the one.
Charleston quake, 1886. So again, because we didn't have too many things out there in the Atlantic in 1811 and 1812, and in 1800s at all, they didn't even know about the Mid-Atlantic Ridge. Now we do. And what we have learned is these things kick off some serious quakes. And it affects all of the other plates. It emanates outward, like energy goes outward, right? So that's why I think Virginia banging hard, because the Atlantic was really banging. So I gotta wonder what's happened. California got a 6.6, and that's the quake we're talking about here in December. So Virginia popped in December at a 4.5, and then California, and then there's a central Mid-Atlantic Ridge right before California, 6.6, right before it. Wow, look at that. December 21, the other one happened, California happened on the 22nd. Then the Panama to Costa Rica border popped with a 6.5, right? Then the Loyalty Islands went really crazy. Wow, that's way on the other side of the world, though.
Yeah.
So it's I want to see where I'm going to pop into the next year.
Yeah, well, 2004 is when the last 6 was on at Parkfield. And 2004, at the end of the year, was the big one.
All right, hold on. I don't know yet because okay, Mexico, Guerrero, Mexico, which is central Mexico on the shore, the western shore, 6.1. Power outages occurred in Mexico City. Loyalty Islands are still doing its thing, of course. Another 2.2 and 2.2. Why do they even have that here? Slovakia, Algiers. I don't know where Algiers is. That Africa or is it on? Or
Algeria.
Okay.
Straight at Gibraltar.
All right. Where's this one? Mid-Atlantic Ridge again, 6.2 on January 16. And then, Mag 261 struck the South Pacific Rise, right? So still banging the South Pacific Rise. That's crazy. February, Panama had a 6.1. Papua, Indonesia, Pakistan, South Sandwich had a 6.6. Wow. I'm looking at, I don't know all the flags in this world, man. Let me tell you. In March, in March we have Nicaragua with a 6.2. Again, that's in a mid-Atlantic coming in right after that, a 6 in March, early March. So the mid-Atlantic and the Caribbean, the Rat Islands, all of the north side of the Pacific Ocean, diving down underneath Kamchatka, creating all these crazy quakes from southern Japan, where the volcano islands are, all the way into the Rat Islands, that whole corner of where the Pacific is being pulled underneath because it's diving on there quite a bit. The weight on that end is now pulling the Pacific that direction. And as it does, it pops the mid-Atlantic because the North American plate can move with it because everything's getting subducted down over there. As the larger scheme of things here. In April, Chile Rise pops with a 6.4. So we were talking about the South Pacific, and now we're talking still the South Pacific, but now a 6.5, leading into Chile. Kamchatka, Russia, 6.2. Costa Rica, 6.2. In May, we're going out a year, one a year on either side. So, not seeing anything. Russia again, 4.9. Magna 6.4, Western Indian Ridge. And it might have just decided to go that side. Kamchatka again popped with a 6.9. Jeez. And it should Prince Wales Islands, which is way down in the south of the Atlantic. And that's a 6.8. No. That's up there, Haida Gwaii. Okay, Prince Wales, 6.8. That we haven't seen that in a while. That's north of Haida Gwaii, Canada. Well, that's interesting. So big quake there. Russia again, Slovenia 5-2. I don't know where the hell that is. New
Already
Zealand.
happened at the end of the year.
And there's another Canadian quake, a 6.4. Two Canadian quakes, two large Canadian quakes. So Prince Wales Islands, a 6.8, and then Vernon, Canada.
Yeah.
Up by BC. Yeah,
Yeah.
up to BC.
Yeah, northern
Um,
BC.
Pacific Antarctic Ridge again, 6.0 in August. Alaska, 6.0. Chile popped with a 6.5. That makes sense because of all the stuff that's happening in the south there on the EPR, East Pacific Rise. Into September, Honshu, Japan got a 7.2. Honshu, Japan got a 7.4. Whew. Big quakes. South Sandwich popped with a 6.9. Wow. Argentina did a 6.4. And then Kaliningrad, 4.8. That didn't really affect us. 6.0 in Northern Cal, Parkfield.
Yep. Because that was the last Parkfield 6 was 2004.
Okay.
So less than a year after San Simeon.
Right. Tokyo popped with a 5.8 in October. 7.0 Nicaragua. Uh-oh. What's going to happen? 6.6 Japan. 6.1 Japan. 7.0 Japan, Hokkaido. Oh, my gosh. November, Vancouver Island, 6.7. So the same year, we got 3 6s in on the west coast of Canada. It was in the north. It popped a little bit south. It popped a little bit more south. 6.7 in November. And Colombia has 7.2. Uh-oh. What's going to happen now?
Well, I know what happens in December.
Yeah, I'm not there yet. Easter Island is 6.6. Got to watch Alaska. December. I don't know what Bermuda is. That's not anything. Hokkaido popped with a 4.5. Cayman Islands. Oh, all right. So that's off Florida coast. A 6.8. Got my arm all wrapped up. 8.1 in the Macquarie Islands underneath New Zealand. Then a 9.1 Sumatra. Holy smoke, all this.
Yeah, so the San Simeon quake was a year before the big one.
Uh-huh. Then a 7.2 in the Nicobar, which is adjacent to it.
Yeah.
Wow.
Which is like one of the aftershocks too. 9.1. Which was the big Indo quake and tsunami.
No, due to the cluttering of aftershocks after the 9.1, we only posted one other earthquake, but there were tons of them. So that's what happened in the 2 years. Now, I don't think we did the year before, did we? 2002?
No, we never did 2002.
But it wasn't a year because it was in December that we're talking about. So we went from December all the way back to January. And then we did December all the way to the next December. So in those two periods, you can see a consistent blast of what's going on in the Pacific Plate. Wow. And how it affects all around the plate. Amazing. Even the Mid-Atlantic Ridge was really active. And because of that, it spread both directions now. It went west and it went east. As it went east, you know what it did, the 9.1, which I think I just played that. No, I did the Japanese one.
Yeah,
9.0.
2011
Yeah.
video. But same idea. Because
Yeah.
2004 was the big.
When you have an earthquake lasting 6 minutes, that's pretty freaking insane. You know, it's like it ain't gonna stop. You know, jeez.
Yeah. So that was, we figured out where the 2003 San Simeon quake came from. So now we get the other famous one that's from that same area, which is
1983.
Coalinga.
Right. 1983 Coalinga earthquake struck at 4:42 Monday, May 2nd in the year of 83, of course. The shock was felt from greater Los Angeles area north to Susanville and Lassen County. Between the Pacific coast and the western Nevada, more than 5,000 aftershocks occurred, which 894 were magnitude 2.5 or up. It measured 6.2 on the moment magnitude scale, maximum mercantile intensity of a 7 or severe. The Coalinga quake. Yeah, 1983. Okay.
I keep reading because it's the same thing.
Yeah, the Coalinga quake was, which caused by a 0.5 meter uplift on the anticline ridge. That's the uplift, by the way. Anticline is up, right? Yeah. You can see that image. See how it's the rising up right there, the basement rocks. And you can see exactly the mountains. Now that shows a better image than what I was trying to draw. Okay. You see these lines here, these mountains here. See how the basements are pizza boxes side by side. This is an anticline. Right here in the center is lifting up. As it's lifting up, it's lifting all these up. That direction and then that direction. Right? But it's lifting up. That's what's happening all over the place. Right? That's anticline. The structure of an anticline is typical fold, that arch-like shape that has its oldest beds at its core, whereas a syncline is an inverse of an anticline. The typical anticline is a convex up which the hinge or crest of the location where the curvature is the greatest, and the limbs are on the sides are fold that dip away from the hinge. Anticlines can be recognized by differentiated from antiforms by a sequence of rock layers that become progressively older towards the center of the fold. Therefore, if the age relationships between the various rock strata are unknown, the term antiform should be used. However, if it's not, then you use the other one.
Yeah.
All right.
So another blind thrust fault quake. Imagine that.
The progressive age of the rock strata towards the core uplift center are the trademark indications evidence of anticlines on a geologic map. These formations occur because anticlinal ridges typically develop above thrust faults during crustal deformations. The uplifted core of the fold causes compression of the strata that preferentially erodes to a deeper stratigraphic level relative to the topography lower flanks. Motion along the faults include both shortenings and extension of the tectonic plate. Usually also deforms the strata near the fault. This can result in an asymmetrical or an overturned fault, and that's what's called the blind fault. Yep.
It's the same thing again back in 83, just they didn't know.
So 83 is the same thing, a thrust fault. Well, an uplift, right? An anticline happening, and then all the side, like I said, the pizza boxes on either side, going to the left, going to the right. Yep. Yeah, boy. The earthquake triggered thousands of rock falls and rock slides, which anticlines also create landslides, right?
Yeah.
34 miles northwest and 16 miles west of the epicenter. Only few slope failures occurred of the epicenter because of the absence of steep slopes. However, that is not indicative of what's happening on the ocean. Very steep slopes causing greater landslides.
Yeah, so that's 40 years ago, and the aftermath, it says this is when they started getting worried about all these unknown faults that they weren't, that they didn't know about. So they're trying to
1983, yeah.
yeah, which is all this new stuff that we just talked about tonight. That's what they're still doing. So 40 years later, they're still trying to figure it all out.
May.
Yeah.
All right, so I'm gonna go
That
to.
was in May, so we're gonna do.
I'm gonna do 82. 82 from May.
Yeah, and you'll see all the exciting earthquakes by me.
So we're gonna talk of we'll go to we're starting January. Yeah, New Brunswick had a 5.7. Hey, I don't know if he felt that one, but that's where my boy Canuck lives.
Yeah.
You remember that one?
Yeah, I was in the same room that I'm sitting in right now.
There were two, 5.7 and a 5.4. Wow.
Yeah, the aftershock, I was downstairs for that one. It was by supper time, I think.
You're no virgin then.
Yeah, so I felt
right.
both of them.
Yeah. Honduras popped with a 6. I wonder what led up to that. Let me go 1 year back. I want to see if something led up to that the eastern side of Canada, right?
Well, I know what was happening in Iceland. But...
All right, that's fine. I don't know yet. So, Japanshu. I'm just gonna zip through it here. Rat Islands, Algeria, France, Greece. God, Greece again. Greece. Chile, Peru. Southern Cal had a 5.8. Westmoreland. Why do I think it's not that? Ecuador 6.4. Peru 5.2. Looking for anything in like Europe so much. Here's France 6.6. Oh, it's loyalty. Forget about it. Chile, Colombia 5.4. Mexico, Guerrero had a 7.3. All right. November.
Well, figuring out my quake is how I got onto the Iceland thing in the first place.
Right.
Because Hekla was erupting that year, and there was 2.
Right. I didn't see any big quakes
in southwest Iceland at 400 kilometers, which they hardly ever get deep quakes in Iceland.
All right. It didn't show on the list, so.
No, because they were only 4s.
Right.
But there's 2 400-kilometer deep quakes in.
Oh wow.
July 81, and Hekla was erupting too.
Yeah, well, it makes sense. So Canada pots with 2 goodies in January there. Greece again's in the middle of that 6.8. Oh my God. Honduras a 6. February.
And New Hampshire had a quake a few days after we had the quake too. And
I didn't see it.
It was a 4, so it's too small to be on there.
Oh, he putzes.
Yeah. And I followed them. They went right down the Appalachians to the end of
Guatemala 6.5. Honduras 5.
Alabama.
June. Oaxaca 6.9. Mexico. Guerrero 7.0. El Salvador 7.3.
So you're seeing what it's doing. It's
Panama 6.8. Ecuador 6.1. Peru 6.3. Honduras 5.5. Like in my mind, I'm visualizing where all these quakes are too. Ecuador 6.6, Peru 6.7, December. Cuba 4.5. That's interesting there.
Yeah. So now you got to get back into 82 again.
Yep. I just did 82. Chile 6.0. What were we looking for, bud?
Well, you went back into 81 too, but so now we did everything in 82. So now we got to go back into 83.
Oh, okay. 83.
Because we're looking for what led up to May.
Right. 83. Yeah, what led to May.
Yeah.
Oh, this is the wrong one. Sorry.
Yeah, because now you
All
got to
right,
get
January. Bolivia 6.3. There's Greece at 7. Oaxaca 6.3. Alaska 6.5. Chile 6.9. Into March, Venezuela came in with a 5.9. It's up sucker. So that's the Caribbean right there.
Yeah.
And the Texas Liniment too, by the way.
Yeah.
Greece, Colombia 5.5. April, Costa Rica 7.1. Oof. Not good. Peru 7.0. La Pica. I don't know where La Pica is. Hokkaido had a 6.5. California 6.7 to Coalinga quake. Again, I said 6.7. That's what the LA quake was. I've hit the wall. My brain is just starting to shut down.
Yeah. So that was the lead up to it. So it was the same thing again. If you go back a year, Mexico was going off, Caribbean, Central America.
Katla.
Yeah.
Katla was going off, you said.
But no, not this time. Central America.
Well, you said New Brunswick. When New Brunswick was going, Katla was going.
No, Hecla.
Hecla. I apologize. It's one of those la ones. Okay.
Yeah, because Katla hasn't gone off since 1918.
Okay.
Last time it went off in the 19th century.
6.5 in Costa Rica.
20th century.
Yeah. Shetland's at a 6.9.
Because I found out whenever Hecla goes off, New Brunswick gets a notable quake. Look at that time.
Alaska again, 6.4. Champa, 6.3. October, Chile, 7.4. Idaho, 6.9. There we go.
Yeah.
We got
that big Idaho quake was that same year afterwards.
So the 6.7 that happened in Coalinga, now in Idaho, we got a 6.9.
Yep.
I don't know what happened the next year, though. What happened the next year? 84. I don't know. I was drunk. The whole year I was drunk. That's when I graduated. I don't know how I did it.
I don't remember what happened in 84, but I know it was the year before the Mexico City.
Well, their format changed. God bless it. Wait, what happened? Oh, look at that.
Yeah. 84 was the year before the big Mexico City quake in 85. I know that.
All right.
And then we already talked about 86 and 87 and all that before when we were doing the other
episode. In April 84, Morgan Hills, California had a 6.2.
Well, that makes sense.
and that's it, because they don't have a listing. All
Yeah.
right.
Dig more to find out what happened in '84. I think that's when Michael Jackson was just getting popular.
84? No, he was already popular.
Because it was grade 4 and 5 for me. Everybody started freaking out over Michael. So
No, that's when he made with the blind guy. Not Ray
Stevie-
Charles, but
Stevie Wonder.
Stevie Wonder. Yeah, they made that songs. Yeah, I'm just putting them in there for our. This is the Wayback Machine.
Yeah, we started out in 20 years ago and we went 40 years back. So
Yeah.
again. Well, last episode we were in the 1800s. So at least now we're in the.
Yeah, this time we went in the 1900s, didn't we?
Yeah.
Yeah, pretty close. 40 years ago, what was going on? We also were, we were back a little bit further than that.
No, that's not to say there wasn't a whole bunch of quakes in the 1800s up in the same area that we're talking
So
about.
do you feel we summed up this? I think we didn't go into all naming of all the faults. I think we went into the fault system and how it all works.
Yeah.
I feel,
we didn't do all the individual faults because we'd be
Right.
here till
be here
and
in
a lot
an hour or 2 hours. Yeah.
a lot of them they don't
So-
have like super lot of studies on each individual one. Anyway.
Right. So next Wednesday we'll talk about San Francisco.
Yeah.
And we'll name all the faults, the major fault systems that work through there, and where they because that'll be on the eastern side of the San Andreas, and we'll go a little bit north up to where the poop cooker is. So
Yeah.
if you don't know where the poop cooker is, then be here next Wednesday, same bat channel, same bat time, and you'll find out how and why United States cooks poop.
And you'll find out about all the quakes in San Francisco, and there was a lot of them in the 1800s. That nobody knows.
Yep. And very, very interesting. I didn't go into it too much, except for how the thrust faults were working, and Canuck was telling us where the thrust faults are, and the whole mechanism of what is going on with the Pacific, grinding up on the northern Atlantic plate, and the angles do matter, and the kind of faults do matter, because the larger scheme of things, and when we start to bring a conclusion to California, we'll summarize all the way through. Like I did a pretty good summary today, but I hope this discussion helps you understand what's going on offshore and onshore, and how these earthquakes are related to one another, and the system behind the invisible system behind earthquakes. And that's kind of what we're shooting for, to help you see what we see. Now, we didn't go into any extra, I don't know, not extracurricular, but extra information that's beyond just talking about earthquakes. We didn't go into storms. We didn't go into anything else, solar or anything. So be aware that there might be other mitigating factors that hasten it or slow it down, or have no effect at all, just kind of coincidental, if you believe in those things. I think you have to have more faith in coincidentals than you do have faith in God.
Like we could end up just doing one quake and do that for like 2 hours and figure all the things out that contributed to it. like all we're doing here now, I'm just showing the quakes are on these faults that we're talking about. Doesn't matter if it's straight slip, thrust, or normal or whatever.
Yeah.
And I give an example of quakes that have happened in these areas that are obvious, and then we can figure out where they came.
Right.
That's all that I'm doing with this now.
Yeah, and the same thing. I'm following right along with you, and on I think together we're able to present the information in a way that is simple enough for even a dummy like me to understand. But anyway, thank you out there, Flutter Girl, Calmness, Quake Cat,
By the time we do every state, you'll find out.
and
It's all
Eden and Timmy. And who else contributed to some of the discussion out here? I often, and Late Girl was out here too. And let's see who we have. Jerpan 56 is out there. Ramblin' Wreck 2718. Yeah. Snow King, Snowplow King, and Susan, of course. And if I didn't call your name, that's because you don't want to have anybody know that you're out there. But I do appreciate you all. Red's probably listening to while he's doing something, or maybe he's sleeping, or maybe he's out on a date. I don't know. Who cares? As long as he's happy. I appreciate you all. Don't forget to also remember to, if you can, leave a gratuity. Type the word or the exclamation point TIP for gratuity, or streamoutlets.com/Joe Slick Live, or you can over there on Rumble, subscribe there, or on YouTube, please subscribe. Look in the live section. You will find on YouTube, you will find all the rabbit holes, as well as on Rumble. On Rumble is they're all listed the same. The newest one will be at the top. The oldest one will be at the bottom. This series of How the West Was Won is listed there from September 1st all the way to the current time, and they've been really like this, just chock full of information, and our anecdotal opinions put in there, of course, and our conclusions based upon our suppositions and how we see things working. It's looking for the mechanism behind earthquakes. That's what we're after. We're trying to understand why earthquakes are happening, not so much in like book knowledge, but in experiential, and looking at the observations of others and what they've written regarding these things, and then trying to put them all together for a larger picture for you, and present it in a way that's easy enough for me to understand. And I'm dense as a brick, so.
And I just put the link in there for the San Simeon quake presentation from.
Oh, great, because that's what we're gonna watch next.
See, I'm even thinking ahead.
Yes, sir. Appreciate you hanging there, Canuck, as we close out the streams. Thank you so much out there in YouTube and Rumble, at Twitch over here. We're going to continue, so hang in there.